Download this code from codegive.com, link in the description below. ECE 459 Lecture 5, Asynchronous I/O Introduction, detailed tutorial with code examples. This tutorial covers the concepts and practical application of asynchronous I/O, focusing on its benefits and implementation in a system like Linux, relevant for ECE 459. We will explore the motivations behind asynchronous I/O, compare it with synchronous I/O, and delve into the programming model using C and Linux system calls. This builds the foundation for understanding more advanced asynchronous I/O techniques. 1. Motivation, the problem with synchronous I/O. Synchronous I/O, also known as blocking I/O, is the simplest and most common form of I/O programming. However, it has significant drawbacks, especially in high-performance or concurrent applications. How synchronous I/O works. When a process requests I/O, example reading from a file, writing to a socket, the process is blocked until the I/O operation completes. The system call, example read, write, doesn't return until the data is transferred or an error occurs. Problem, wasted CPU time. While the process is blocked, the CPU is essentially idle, waiting for the I/O device to respond. This is a major waste of valuable processing power, especially when I/O operations are slow, example disk access, network latency. Concurrency challenges. To handle multiple concurrent requests with synchronous I/O, you typically need to use threads or processes. Each thread/process handles one I/O operation. This introduces complexity due to context switching overhead, synchronization, locks, mutexes, and potentially increased memory usage. For a large number of concurrent connections, managing thread/processes becomes inefficient. Example, synchronous file read. In this example, the read call will block the program's execution until it finishes reading from data.txt. The program won't proceed to print the data until the read operation is complete. 2. Asynchronous I/O, the solution. Asynchronous I/O, AIO, also known as non-blocking I/O, offers a way to overcome the limitations of synchronous I/O. How asynchronous I/O works. 1. A process initiates an I/O operation. 2. The system call returns immediately, without blocking the process. The process can continue performing other tasks. 3. The operating system, or a separate I/O subsystem, handles the I/O operation in the background. 4. When the I/O operation completes, the process is notified, example via a signal, a callback function, or by checking a status. Benefits of asynchronous I/O. Improved concurrency and responsiveness. The CPU isn't blocked during I/O operations, allowing the process to handle multiple requests or perform other computations concurrently. This leads to better responsiveness, especially in interactive applications. Increased throughput. By overlapping I/O operations with computation, asynchronous I/O can significantly increase the overall throughput of a system. Scalability. Asynchronous I/O is better suited for handling a large number of concurrent connections than traditional thread-based solutions. It avoids the overhead of creating and managing many threads/processes. Resource utilization. AIO can lead to better resource utilization by keeping the CPU busy while waiting for I/O to complete. 3. Asynchronous I/O implementations and abstractions. Various methods are available to implement or abstract asynchronous I/O. Operating system specific APIs. Many operating systems provide native asynchronous I/O APIs. On Linux, AIO, PA6 asynchronous I/O, and epoll are prominent examples. On Windows, IOCP, I/O completion ports, is a common technique. Asterisk event loops, like libvent, libov. These libraries provide event loops and event notification mechanisms that allow you to register callbacks for I/O events. They manage the underlying asynchronous I/O primitives provided by the OS and present a higher level, easier to use interface. Node.js uses libov. Asynchronous libraries, like Boost.agio. Libraries like Boost.agio provide cross-platform asynchronous I/O abstractions that simplify the development of asynchronous applications. 4. POSIX Asynchronous I/O, AIO, on Linux. POSIX AIO, as defined by the POSIX standard, is a standardized way to perform asynchronous I/O on Linux. It's based on a set of system calls that allow you to initiate I/O operations without blocking. Key POSIX AIO system calls *AIO_read, initiates an asynchronous read operation. *AIO_write, initiates an asynchronous write operation. *AIO_error, checks the error status of an asynchronous I/O operation. *AIO_return, retrieves the return value, number of bytes read/written, of a completed asynchronous I/O operation. *AIO_cancel, cancels a pending asynchronous I/O operation. *LIO_listio, initiates a list of asynchronous I/O operations, read and/or write. Data structures The central data structure for POSIX AIO is struct IASIB, asynchronous I/O control block. This structure holds all the information needed to perform an asynchronous I/O operation, including *AIO_filters, file descriptor for the I/O operation. *AIO_LIO_opcode, type of operation, LIO_read, LIO_write, LIO_NOP. Used with LIO_listio. *AIO_recprio, request priority, currently ignored on Linux. *AIO_buff, pointer to the buffer for the I/O operation. *AIO_nbytes, number of bytes to transfer. *AIO_offset, offset into the file where the I/O operation should start. *AIO_segevent, structure specifying how to signal the process when the I/O operation completes. This allows you to use signals, segev_signal, or a callback function, segev_thread. *AIO_data, user-defined data that is passed back to the process when the I/O operation completes, example a request ID. Example, asynchronous file read with POSIX AIO. Explanation of the code *. 1. Include headers. * includes necessary headers for AIO, signals, and file I/O. _new_ source is required for signal delivery to threads and sometimes for real-time signals. 2. Signal handler, *handler. This function is called when the I/O operation completes. It's registered to handle the sigridmin signal. It receives a siginfo_t structure, SI, containing information about the signal, including a pointer to the IASIB structure. It uses AIO_error, to check if the I/O operation completed successfully. If successful, it uses AIO_return, to get the number of bytes read and prints the data. It exits the program, for simplicity. In a real application, you'd likely signal a thread, set a flag, or perform other actions to indicate completion. 3. Main function *. Asterisk allocate buffer asterisk allocates memory for the buffer that will hold the data read from the file. Asterisk open file asterisk opens the file for reading. Asterisk initialize IASIB asterisk this is crucial. The IASIB structure must be initialized to 0 using memset. This avoids undefined behavior. We then set the file descriptor, offset, buffer pointer, number of bytes to read, and the AIO_SIG structure. Asterisk AIO_SIG setup asterisk this specifies how the process should be notified when the IO operation completes. In this case, asterisk SIGEV_notify equals SIGEV_signal, we want to receive a signal. Asterisk SIGEV_signal equals SIGRETMIN, we want to receive the SIGRETMIN signal, a real-time signal. You can also use standard signals like SIGUSR1 or SIGUSR2, but real-time signals are generally preferred for AIO because they are more reliable. Real-time signals are numbered from SIGRETMIN to SIGRETMAX. Asterisk SIGEV_value.civil_PTR equals and AIO_REQ, we pass a pointer to the IASIB structure as part of the signal. This allows the signal handler to access the IASIB structure and retrieve information about the IO operation. Asterisk AIO_LIO_opcode equals LIO_read, specify the operation is a read. Asterisk setup signal handler, SIGAction, registers the SIGO_handler function to handle the SIGRETMIN signal. Asterisk start asynchronous read, AIO_read, calls AIO_read, to initiate the asynchronous read operation. This call returns immediately. Asterisk do other work asterisk the code then simulates doing other work by sleeping for a few seconds. This demonstrates that the process can continue executing while the IO operation is in progress. Asterisk pause, asterisk the pause, call puts the process to sleep until a signal is received. This is where the process waits for the signal from the AIO operation. Asterisk cleanup asterisk the cleanup code, closing the file descriptor and freeing the buffer, is likely not reached in this example, as the SIGO_handler exits the program. In a real application, you would need to handle cleanup differently, ensuring that it's executed even after a signal is received. Compilation asterisk. Asterisk thread, needed for using signals in a multi-threaded context, even if the example appears single-threaded. It's crucial for correct signal handling. The AIO implementation relies on threads internally. Asterisk LRT, links against the real-time library, which provides the AIO_* functions and real-time signals. Running asterisk. Make sure you have a file named data.txt in the same directory. 5. Important considerations and best practices asterisk. Asterisk initialization is critical asterisk always initialize the struct IASIB using memset. Failure to do so can lead to unpredictable behavior and crashes. Asterisk error handling asterisk always check the return values of all AIO system calls, AIO_read, AIO_write, AIO_error, AIO_return. Asterisk signal handling asterisk use real-time signals, SIGRETMIN to SIGRETMAX, whenever possible for AIO notification. They are more reliable than standard signals. Asterisk memory management asterisk ensure that the buffer pointed to by AIO_buff remains valid and accessible until the IO operation completes. Do not free or modify the buffer while the operation is in progress. Asterisk file system support asterisk not all file systems fully support asynchronous IO. Test your application thoroughly on the target file system. Asterisk kernel configuration asterisk asynchronous IO requires proper kernel configuration. Ensure that AIO is enabled and that the maximum number of AIO requests is sufficient for your application. Asterisk cancellation asterisk use AIO_cancel, to cancel pending IO operations if they are no longer needed. Asterisk thread safety asterisk if you are using AIO in a multi-threaded environment, ensure that your code is thread safe. Use appropriate synchronization mechanisms, mutexes, semaphores, to protect shared data. However, one of the goals of AIO is often to reduce the need for explicit threading. Asterisk alternatives asterisk consider using higher-level asynchronous I/O libraries, libvent, libov, boost.agio, if you need cross-platform compatibility or a simpler API. Asterisk LIO_listio, asterisk the LIO_listio function allows you to submit multiple AIO requests simultaneously. This can improve performance by reducing the overhead of individual system calls. It can also be used to coordinate multiple I/O operations. 6. Comparison with synchronous I/O and threads. Feature synchronous I/O asynchronous I/O threads, with synchronous I/O. Concurrency limited high. Blocking yes no yes, per thread. CPU utilization low, during I/O, high potentially high. Complexity low moderate high. Scalability poor good limited by thread overhead. Resource overhead low high, thread context switching. When to use asynchronous I/O asterisk. Asterisk high concurrency applications asterisk web servers, database servers, network proxies. Asterisk I/O bound applications asterisk applications that spend a significant amount of time waiting for I/O to complete. Asterisk real-time applications asterisk where responsiveness is critical. Asterisk applications that need to handle a large number of concurrent connections. When to use synchronous I/O or threads asterisk. Asterisk simple applications asterisk where concurrency is not a major concern. Asterisk applications where I/O operations are infrequent. Asterisk when you need to leverage existing code that is written for synchronous I/O. Asterisk when asynchronous I/O is not supported by the operating system or file system. 7. Advanced topics, beyond the scope of this introduction. Asterisk kernel AIO versus user space AIO asterisk true AIO requires kernel support, where the I/O operations are handled directly by the kernel without blocking the process. Some implementations provide user space AIO, which simulates asynchronous I/O using threads or other techniques. Asterisk direct I/O, O_direct bypasses the operating system's buffer cache. This can improve performance in certain cases, but it also requires careful handling of data alignment. Asterisk memory mapping, map provides a way to map a file into memory. Changes to the memory mapped region are automatically written to the file. Conclusion. Asynchronous I/O is a powerful technique for improving the performance and scalability of I/O bound applications. While the POSIX AIO API can be complex, understanding its principles and mastering its usage is essential for building high-performance systems. Remember to carefully consider error handling, memory management, and signal handling when working with asynchronous I/O. This lecture provides a fundamental introduction to the topic, and further exploration of the concepts, system calls, and best practices will enhance your proficiency in developing efficient and scalable I/O intensive applications.